All right, in the last time or two, we've been exploring the thermodynamics of binding with a special focus on the fraction bound of, say, a protein binding to a ligand. We stopped last time before we did this example problem, so let's do that now, and then we'll move on to a very useful topic that goes under this area called a scattered analysis or a scattered plot. All right. So the problem says at 300 Kelvin, for a ligand concentration of 0.2 micromolar, the fraction bound to P, so PL, is 0.05. What is Kd at this temperature? 0.5, not 0.05. Did I say 0.05? I can't remember. What is Kd at this temperature? So that's number A, or part A. Let's look at that. First of all, F is equal to a half. When F is equal to a half, the ligand concentration is equal to the Kd. The ligand concentration is 0.2 micromolar, so that's 2 times 10 to the minus 7. So at 300 K, the Kd is 2 times 10 to the minus 7. Part B says as at 310 K, raising the temperature by 10 degrees, keeping the ligand concentration the same, the fraction bound to P is 0.9. What is Kd at 310 K? In this case, we know the fraction bound. We know the ligand concentration. We have to solve for the Kd value. That's a matter of doing some algebra. So first 1 over that, and then subtract 1, and then multiply through by L, and you get that Kd is equal to L times 1 over the fraction minus 1. Plugging the numbers in, L is 0.2 times 10 to the minus 6, 0.2 micromolar that is. The fraction bound is 0.9, and you get 2.2 times 10 to the minus 8, which you notice is just a little bit more than 10 times bigger than the Kd at 300. So this is the Kd at 310. And therefore we have the Kd at 2 different temperatures, and that leads to the third part of the question, which says, what are the delta H and the delta S for this reaction? So since we have the K value at 2 different temperatures, we can do a Van 't Hoff analysis. We can calculate the delta H for dissociation, right? So not the delta H for binding, but the delta H for dissociation, because we're using Ks for dissociation, Kd values. That's equal to minus R log of the ratio of the 2 Ks divided by the difference between 1 over the temperatures. And that's 8.314 times 2.2 times 10 to the minus 8 over 2 times 10 to the minus 7, 1 over 310 minus 1 over 300. And that gives minus about 170 kilojoules per mole. Notice a negative value of the delta H for dissociation, which means that dissociation is exothermic. That means binding is endothermic. So this delta H value that we're getting here is large and unfavorable to binding. It's favorable to dissociation, in fact. And notice also, remember our rule of thumb, that if delta H is around 50 kilojoules per mole, then a 10-degree difference in temperature will cause a factor of 2 in the equilibrium constant. But here, a 10-degree difference caused a 9-fold change in the equilibrium constant, and so we expect a much bigger number than 50 kilojoules per mole, and that's what we get. In fact, we get 170 kilojoules per mole, more than 3 times bigger. So since this is the delta H for dissociation, the delta H for binding is just the negative of that, plus 170 kilojoules per mole, a very large, unfavorable, endothermic delta H for this binding reaction. We can now use our standard approach to calculating the delta S of dissociation again. We use the delta H of dissociation, and we use the delta G of dissociation, which is minus RT log of K of dissociation at whatever temperature we like. Let's choose 300 K. And so we get delta H of dissociation divided by 300 K plus R log of KD at 300 K Plugging the numbers in, minus 169.9 over 300, plus 8.314 log of 2 times 10 to the minus 7. And that gives us a negative 694, a very large negative delta S of dissociation. In other words, what this reaction is, what these numbers are telling us is that dissociation is large and exothermic, and its delta S is very unfavorable. There's a lot of loss of entropy when you dissociate. That means, though, that the delta S of binding is the negative of that plus 694.5 joules per K per mole. And so, what this overall set of data is telling us is that the binding is very strongly driven by the delta S, by a big increase in delta S upon binding, big enough to overcome the large unfavorable delta H of binding. So even just two numbers, calculating the fraction bound at two different temperatures, is enough to give us some very important clues on what the nature of the binding is. And that's true not just for this makeup example, but in real life too. All right, that leads us to the next topic, which is scattered plots or scattered analysis. In very many cases, you have some sort of binding reaction like this, and you want to know what the KD is. But in biological settings, you very often don't even know what the binding protein is or the binding molecule is, let alone what its molecular weight or what its concentration is. If you don't know its concentration or its identity or its molecular weight, if you hardly know anything about it at all, can you still get the KD? You know it's there, you know something is there, you know something is binding L. Is that enough to get the KD? It turns out using scattered analysis, it is enough. So let's see how that works. In order to use scattered analysis, you have to be able to measure or tell when the ligand is bound and when it's not bound. We'll talk in a bit down below how you would go about that. Let me just preface that with by looking down here. Here's one way. You have some unknown protein that binds to some ligand. You have a known concentration of the ligand. You mix it with the unknown protein. And then you put in some activated charcoal, which absorbs and removes from solution all of the unbound ligand. And then you pellet all that charcoal out. So now you've separated all the free ligand from the bound ligand. You can put if the ligand is radioactive, you can put this in a scintillation counter or something like that, and you can tell how much bound ligand there is. So that's, just physically separating the free and bound ligand with some kind of thing like activated charcoal is one way that you can tell free from bound ligand. There are other ways too. Sometimes when a ligand binds to a protein, its fluorescence changes. In that case, you can just monitor fluorescence and tell how much of the ligand has bound. All right, so we can therefore, in principle, in a lot of cases, measure how much free ligand there is and how much bound ligand there is. I'm going to simplify notation by saying that the symbol L here means L free. That's the free ligand concentration. And the bound ligand we'll call L sub B. All right, so we have our equilibrium constant expression. These are all equilibrium values of P and L and PL, or activities really. Again, we're simplifying things so that activities become molar concentrations. The PL concentration is the same thing as the ligand bound, right? If the ligand is bound, then it's bound to a P, and so that's the PL concentration. The free P concentration is the total amount of P present in solution, which we don't know, but there's some value to it, subtracting the amount of PL, which is the bound ligand. Plugging those numbers in, we get that KD is equal to P0 minus the bound ligand times the free ligand divided by the bound ligand. And now a little bit of algebra. We move this ratio of free ligand over bound ligand over to the other side of the equation. And then we divide through both of the remaining terms by KD. And that gives us the scattered equation, which is the basis for scattered analysis and scattered plots. It says that the ratio of the bound ligand to the free ligand is equal to a slope times the concentration, presumably known, of the bound ligand plus an intercept, which in fact we don't need to know. The intercept depends on this unknown concentration, total concentration of P, but we don't in the end need to know that because it's just the intercept. What we really want is KD, and that's the slope, and we can get the slope without knowing the intercept or even worrying about the intercept. So what that says is that if we plot this ratio of bound to free ligand as on the y-axis versus the bound ligand concentration as we change the bound ligand concentration on the x-axis, we should get a straight line. This is an equation for a straight line, and the slope of that straight line will be -1 over the number we want, the dissociation constant for the protein. Notice that this is equal to minus the association constant also, so which is also equivalent to knowing the dissociation constant, and also a very nice quantity to know. So we make a scattered plot like this, find the slope, and that should tell us, I mean, it looks really simple, that should tell us what the KD is. So we looked at this a little bit already. We see that you can, in principle, measure the amount of bound ligand and separate that, and you know how much total ligand you put in to start with. That's something you have control over. So that tells you how much free ligand there is too. And so here's the kind of thing you do. You make a plot of the amount of bound ligand along the y-axis versus the total amount of ligand that you put in, right? And that gives you something that looks like this red curve. You do the same thing on a control sample to account for non-specific binding, right? The ligand may bind to things other than the protein that you're interested in. You've got to account for that somehow. You subtract the green guy from the red guy, that gives you this blue guy or black guy, and that is a plot of the bound ligand as a function of the total ligand. Now you can subtract the bound ligand from the total ligand, get the free ligand, use that to calculate the bound to free ratio, put that on the y-axis, plot that versus the total amount of bound ligand, and that should give you your scattered plot with a slope of -1 over KD. Let's do an example. And to do that, I'm going to go back over to the old notes over here. So here they are. Here's some data. This is made up data. I don't want to give anybody the impression that this is real, actual experimental data. No, this is made up so it's going to be perfect. It's going to work well. Here is the total amount of ligand that we put in. So we're varying that. That's something we have under experimental control, right? 2 molar, 4 nanomolar, 6 nanomolar, 8 nanomolar. And then we're starting to approach, we want to get to saturation so we can kind of tell how much stuff is there. And so we jump from 8 nanomolar here up to 100 nanomolar and then to 200 nanomolar. And at each point we measure how much bound ligand there is, so about 0.3 nanomolar, 0.5 nanomolar, 0.6 nanomolar, 0.6.5 nanomolar. You can see that things are slowing down because we're starting to saturate a little bit. By the time we've gotten to 100 nanomolar here, we're really saturating. Almost all of the ligand is bound. And by the time we go up to 200 nanomolar, it's clear that not much change has occurred because we've already saturated at this point. All right, now we subtract this guy from this guy in order to get this guy, the free ligand. And here are the numbers, 1.7, 3.5, 5.4, and so on, all nanomolar units. And then we make the ratio of this guy divided by that guy. That's our bound over free ratio. And here's the numbers. Now we make a plot. So we plot the ratio, that is the numbers in this column, versus the total amount of bound stuff, which is the numbers in this column. And we do indeed get something like a straight line. I guess I put some noise in there because it looks like it's not a perfect straight line. I didn't just calculate these numbers out. I must have put a little bit of noise in there. And we calculate the slope. In this case, its slope is delta y over delta x. So we're taking the difference between two numbers along the y-axis here and dividing them by those same two numbers along the x-axis. So this is delta x, this is delta y. And that gives us a number, it's going to be a negative number because you've got a negative slope here, obviously. Minus 0.248 units of nanomolar to the minus 1. Notice that on the y-axis here we have a unitless number. So this numerator here is unitless. The denominator has units of nanomolar. And so we're going to get units of nanomolar to the minus 1 for our slope. And 1 over that, or minus 1 over that, is the KD value, which turns out to be 4.0 nanomolar. So that's an example of a scattered analysis. And in this case, we could use the intercept if we liked in order to calculate the amount to actually find out how much of the ligand was present, and we get 1 nanomolar in this case. Again, the problem was set up that way. All right, that's scattered analysis. A very standard technique that you'll see over and over again in the literature. And I think I will stop there and make another video because the next topic is a rather long one.